I'm not sure how good that will be, but try that. So today we will continue with what we did yesterday. We were doing Little's theorem. And let me just rewrite it again. Which is the expected number of people in the total number of people in the system is equal to lambda times the expected number of time that they're in the system. So I put in what all these things are more explicitly. So n is total number of people or whatever in the system. Capital T is total time that a person is in the system. And lambda is the arrival rate on average. This we did yesterday, and we'll do another example in a second. But what we want to do today is to add in a couple things. A little aside, on the written notes that I'm going to put on Blackboard, I'll actually give a rough proof of this if you're interested. I'm assuming most people are not, so I won't do it here. So what we add in here is two things. It doesn't let me erase, so sorry about the crossouts. So the first one is we're going to have NQ, the number in line. So there'll be some people who are being served by the server, and now also some people waiting. So NQ will be the number waiting. And W will be the number of people in the amount of time that a person is in line on average. So what we're going to want is we have the E of N and we have the E of T. We want to get what is E of W and E of NQ. Okay. So a little thing here with this little whiteboard is it doesn't save them. So when I say to erase something, it clears it just like a regular board. So I'm going to be pausing every once in a while just to check, see if people have questions, and then I'll erase and go to the next board. So before I erase, any questions on this? Really just delaying so you have time to write stuff if you want. Okay. So let's do this with an actual example. So erase. But before I do, let me do a little note. Is one extra variable that we're not going to use much, but it's kind of in the background, is the total time of the system is equal to the amount of time we wait in line plus the time it takes us to be served. As we said from the beginning, S is exponential. Parameter mu. So we don't use it for now, at least. But that would be the density function for it. And so unlike the other ones, this one we can easily get which is we know that the exponential has an expected value of 1 over the parameter. So we know that E of S is equal to 1 over mu. So the relation between T and W since we know that E of a sum is the sum of the expected values, we can break it up into E of W plus E of S, and we know E of S is equal to 1 over mu. So now let me go to the actual example. We start with our nice easy one, MM1. So this is just the one server. With nice easy numbers. And let's review. Let's find the steady formulas. Probabilities. So we have the formulas, which is what I started writing, from yesterday and Monday. So we don't have to go from the beginning like we did the first time. So this is going to be hard to write, but anyone able to say what the expected value is, what the probabilities are? So pk is equal to in general that. So in this case, let's start just getting in numbers. We actually won't need these, but what is P0? Therefore, in this case, check everyone's phone. Make sure someone can hear me. So, can someone hear me? Thank you. Okay. So what is P0 here? We're just plugging in. That's going to be that first part, the one slammed over mu. And then again, plugging into the formula. So we don't have to do any work, we can just use the formula plug. We're not actually going to use this for the rest of the problem. So when we now go to the next one, I don't worry too much about erasing this, even though we can't get it back. But let me ask here, are there any questions? And again, I'm delaying because I'm going to erase and start again. So let me do part B. Again, something we had done. Let's find E of N. So again, we have a formula for this, and then one is nice. That. So in this case, what do we have? So here lambda is lambda 2, so it's 2 over 3 minus 1. And you get 2, so 2 people, 2 whatever. So that we have a formula for. We also have a formula for this. And we can do this in one of two ways. We can either use Little's theorem, or equivalently, we have done this in general, and I found that that was true. So again, just plug in we get that is 1. The average time is 1. So those two we did yesterday, so nothing new, maybe even Monday. So now let's add in the two notation ones, the two new ones. Find E of W and E of NQ. So the note from today is we said that E of W is equal to, really the other way around, E of T is equal to E of W plus E of S. Therefore, E of W is equal to T minus E of S, and as I said, S is just exponential, so it's easy. It's just 1 over the parameter, which in this case is mu, and in this case that is 3, so we get the 1 minus 1/3, which is 2/3. And for E of NQ, we can again use Little's theorem. So the idea is Little's theorem works just as well for E of W as it does for E of T. So Little's theorem says E of N is equal to lambda times E of T. Also tells us that E of NQ is equal to lambda times E of W. And so I just multiply by the 2. So Little's theorem works for the time that you wait in line and the number in the line just as well as it does for total time and total number of people in the system. And again, MM1 is nice and easy. So this part is new. So any questions on this part? Okay. Again, as I said, I'm delaying because I'm going to erase in a second. And if you just came in, this is being recorded, and I will put up the notes online on Blackboard, so you will have this in a different form. So let me now do two things that are a little bit different. Do the same thing before, which is let's do a finite one, but now let me do it with more than one server. So that's the example there. And so let's make it MM23, where lambda is equal to 3 and mu is equal to 2. So this first number, the 2, says now we have 2 servers. And so a little thing, which I think I said a little wrong, is it says we have 2 servers. But we only have one big line, and they split when they get to the front. So since this is new, we have to, again, go to the basic thing. So draw our thing and then read off to get the probabilities. And here's our first difference, which is this is still 2, going from 1 to 0. And that's because there is one person, so one server is working. Because up here, when we say mu is equal to 2, this is the rate for each server. Therefore, if I go here, where there are now 2 people, now both servers will be working, and so the rate will now be 4, because 2 people, you can each serve 2 people at the same time, meaning that you can serve 4 people per whatever the time interval is. On the other hand, this is still 4, because even if there's 3 people, there's still only 2 servers, so there's still only 2 servers working, and now someone will be waiting in line. So let me try part of it here. So I'm going to keep it on the same page so we can get it from the next one. Is let's find the steady state probabilities. And remember that you can read these off. You just read backwards. So for example, P1 said we're going from here, and so I look at the ratio to its left, and I get that is equal to 3/2 times P0. P2, again, look to its left, is then 3/4 times P1, therefore it's 9/8 times P0. And finally, P3 is again looking to the left, the ratio is 3/4 P2, therefore it's 27/32. That's supposed to be a 3 before the P2, P0. And now we know that 1 is equal to the sum of all the probabilities. And we'll do the substitution to get that in. So this is new. So any questions on any of these numbers? Oh, and I have a question. So this question from a little while ago from before, so from Michael, which I'll talk about. Yeah, so any questions on this? Notice, even though we have 2 servers, we still are assuming this process that we can only move 1 unit at a time. So if I'm at 2, even though there are 2 servers, I cannot go from 2 to 0. All it means is I will go more quickly from 2 to 1. So again, time will come up later. So again, delaying because I'm going to erase this. So anyone not have this? Okay, erase. Oh, so someone asked if it's 1 equals P0 plus P1 plus P2 is equal to P3. It should, of course, if I wrote that incorrectly, be P0 plus P1 plus P2 plus P3. So this one is like the one we did before. Once we have the problem, I didn't actually find it. So I'll do that in a second. We didn't actually solve for it, so I'll do that. So we have that 1 and 2 P0 times 1 plus, remember the constants we got. Plug in the constants we got from the last one. That's supposed to be a 143, which I'll rewrite in a second. So we have P0 is just reciprocal. And then from the last one, P1 is equal to 3/2 times it, so we get 48. And multiplied by 3/4, so 36. And so, and of course we can double check. Obviously these should add up to 1, which they do. And so then I can bring that up here. So I have 1 times the 48 over 143 plus 2 times 36 over 143, and that gives me And I can do this new thing. What is E of NQ? So N of NQ is, again, the number of people who are waiting in line. So we have to go back and ask for each of the N's, what is NQ? So obviously, if N is 0, there's no one in the system, then NQ will also be 0. If N is 1, there's one person in the store, then how many people are waiting in line? And this is the new part. It actually becomes pretty simple. 0, because one person in the store is being served. And if N is 2, no, there are 2 servers, so they're both being served, and so N of Q is still 0. And finally, the last possibility is N equals 3. There are 3 people in the store, and 2 of them are being served, and so N of Q is equal to 1. So you can see N of Q can only be either 0 or 1, and so when we do the expected value, we do 0 times its probability. I could do the same as I did before. And then 1 times the probability of 1. And I get that. So any question on the numbers for NQ? And as always, you're double checking my arithmetic, so let me know if I got the numbers wrong. Okay, so let me erase. And the last one is the 2 new ones again. Oh, the 2 new ones. So we want to find the time ones. What is E of T and what is E of W? So we know from Little's theorem that E of T is 1 over lambda times E of N. But remember from yesterday that we need the mean arrival rate. And the reason this is different than the last problem, in the last problem it was infinite, so it didn't matter how many people were in the store. Their arrival rate was the constant that was given. Here, lambda is equal to 2. Yeah, 3. If n is equal to 0, 1, or 2. But if there are 3 people in the store, since that's the maximum number, the arrival rate is 0. So we get the weighted average, the values times their probabilities. So when there's 0, 1, or 2, the rate is 3. So we multiply 3 times those probabilities. And then 0 when n is 3. And I get that is that is the average arrival rate, lovely number. And now I can use the Little's theorem, except with this arrival rate. It's a little hard to read that. 67 divided by 116. this one, I actually have two ways I can get EW. So I do both. One is I can use what I did in the last one, which is E of W is equal to E of T minus 1 over mu. And I can also use Little's theorem and E of NQ. Because again, Little's theorem works for W and Q also. So I can do the E of NQ that we got and divide by the lambda A that we just got. And obviously, we should get the same number, so you can double check your work. So I kind of do the usual thing. So someone asks, will you always be given the lambdas? And that is true. I will always have to give it to you. If you start the homework in that first set, there's one where lambda isn't constant. So we will come eventually to one where lambda isn't constant, so it can be something besides 0 or the n lambda. So we will have one where it's changing depending on n, which, if you think about it, is how the real world works, which is if there are a lot of people in the store, then that could mean either fewer people go into the store, so the rate goes down, or it could mean it's popular, so more people go into the store, so the rate goes up. So in the real world, it's going to change depending on how many people are there, and we'll do one like that. Any other questions on this one? I should say, again, just delaying, is this, again, the first time I've done this one, so we're going to go too long today. We will do more, but not the full time. And hopefully I can get a little better at this for the next class for Monday. So any questions? So let me do another example. It's supposed to be infinity. So let's try MM infinity. And again, since there's no last one, it really is fully MM infinity infinity. And let's do fairly simple ones. The arrival rate is 2, and the departure rate is 1. So this one, we have an infinite number of servers. And in some sense, this is similar to maybe how Google would actually work, which is Google is getting lots and lots of questions. And in theory, at least, if the number goes up very fast, they'll just assign more servers to answer questions. And in theory, at least, they could answer an almost unlimited number of questions. So in some ways, they don't really have an upper bound. They, of course, do, either because they don't have enough servers or just things slow down. But theoretically, yeah. So let's do the same thing. Again, we're starting something new. Let's draw it. And we'll start with getting the numbers. As with the last one, for now we're keeping lambda a constant. And like the last one, the first departure rate is 1. And again, that is because at that point we're going from 1 to 0, which means we have one person in the store, which means one server is working, and one server can do one person per minute. So leading off from the last one, what will this number be? Like the last one, it'll be 2. There we go. I should actually wait longer because in my other class there's a bit of lag time with the chat, so sometimes it'll take a little while for me to get answers. So it'll be 2 because now we're reading from here, which means we have 2 people, and that means two servers are working, each at a rate of 1, therefore it'll be 2. Keep going. What will this rate be? And again, reading, I put an arrow in. Going from 3, it will now be 3. And then you can see the pattern, it's just going to keep going up. The next one will be 4, then it'll be 5, and then it'll be 6, and it'll keep going up. Like the last one, we get the relations, and again, we can read off. So at 1, I'll read to the left. So the ratio is a 2 over 1. Again, read the ratio, the 2 over 2. Obviously that simplifies, but for now, I guess I will simplify. So that is the 1 times the 2. So again, 2 P0. P3 is equal to 2 over 3. Again, look at the ratio to the left of 3. And on that, the pattern. Next one will be 2 over 4. And I'm actually going to write this as this. So when I put it in, I get this, and what I'm looking for is a pattern. And if you look at what we're multiplying, so first we multiply by 2 over 2, multiply by 2 over 3, and we multiply by 2 over 4. So we keep multiplying in the numerator by 2, and we keep multiplying by an additional 1 in the denominator. And I get that pattern. 1 plus 2 squared over 2, plus 2 cubed over 2 factorial, plus 2 to the 4th over 4 factorial, plus 2 to the 5th over 5 factorial, and so on. So this is a question. This is, if you remember anything from Calc 2, this is a series you might know. Does anyone know what type of series this is? This is a Maclaurin series for a what function? Anyone remember? I think we did it way back when we were doing moment generating functions. Yep. So someone said e to the x. So we know that e to the x is equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus dot dot dot. Therefore, what does this add up to? Just put in x. Equal to e squared, because if you compare them, x is equal to 2. And I didn't quite have enough room for the rest of it, so let me again ask to delay because I'm going to erase this. Any questions on this? I should say, think back to when we were doing moment generating functions. I said, and it's still true, that the only infinite series that you need to know is the geometric. So you should know this, but you don't need to know it for now. So let me erase, just finish this one off. So that would give us P0 is equal to e to the negative. And then using the relation, move down to P1 and P2 are the same. They're both e to the negative 2, and we get P3 is equal to something, and we keep going. So I ask again, this is what I asked about it. Can people hear me? So I'll move slightly around, see a couple times. Okay, how is it now? Yeah, it happened this morning too. Alright, so we're going to try again. How is it now? Can anyone hear me? No. Okay, so let me switch back and see if it helps. So you'll see something that you don't care about. Alright, well, in some ways I'm going to mostly stop now. So it kind of works out because from here, actually I think I'm sort of a bit to take this out. So it works a little better now. Can people hear me? Yes, no? No. Move stuff around again, see if it's just in the way. So, how about does it sound better? My guess is it's the connection. Same thing happened this morning that for a while nothing worked. So some people are saying they can't hear and some say it's muffled. So can you understand what I say? Because I'm mostly going to finish. We're mostly finishing, so can you understand enough when I say things, or should I just write everything? So talk or write. So now someone says it is okay. Okay, so mostly we're going to be done. As I said, it probably is the connection went out. So in theory, we get E of n, but we would need derivative of the Taylor series. So if you want, you can try that, but you wouldn't need to do it. So let me just talk about what's going to happen from here, which is, as I said yesterday, we obviously don't have a quiz, but you have the quiz, and you can treat this one of two ways. You can try it on your own. You can send it to me as a grade it as if it's real, and give you what you would have gotten for a grade, and Monday I'll put up the answers. Second thing is I'm not quite sure what to do with the quiz and test, so I'll probably push that back a bit. So you can try the quiz, send it to me with a PDF. I'll grade it as if it's real, but it's not. And I'll put up answers for the quiz review, the quiz that you got yesterday, on Monday. There will definitely be one or two take-home quizzes, because those, I don't care where you are or anything, it makes it easy. I just give it to you and say, like the computer lab, in a week, you're going to hand it in, and you can work in groups and so on. So there'll be one or two of those, because those are pretty easy. What I might do for the test, which I think I said yesterday, is in a couple weeks, I'll say next Thursday at 12 o'clock or 1 o'clock or whatever time, I'll put a copy of the test on Blackboard, and then I'll say, you need to get the answers to me within 90 minutes. Give you a little extra time because it'll be a pain. For the weekend, you can start looking at from that first, so the Q's handout is broken up into a few pieces. Try working on that first set. And we'll do a couple of those homeworks on Monday. Okay, so that's it for now. As I said, because it's the first day, I assume this is going to be messy. So let me stop a bit early, but I will stay on for a couple minutes if you have quick questions. Otherwise, I'll try this again Monday. Hopefully with more practice, it will go a little bit better. And I might try putting in some video and or slides so that you can see some things a little bit better. So one person asked, so two things. So one is, didn't hear about the next quiz. I'm not sure when it will be, but the next quiz will be a take-home quiz, which means when you get it, you'll have something like a week to do. So that is not immediate. I will probably hand it out at the earliest next Thursday, because I'll take some time to get things ready. So someone asked about the notation for Q's. So let me do it again. This is supposed to be an M. So the B is for births, which is entry. For us, we assume that people are going into the store randomly. And if that is true, that's supposed to be the word random there, then it is a Poisson distribution. The D is for deaths or departures. If the entry is Poisson, then it means that the departure rate will be exponential. And if those two go together, and that's where we get the MM. So MM says that the people entering are entering randomly according to a Poisson process, because those go together. And if the entry is Poisson, then the departure rate is going to be exponential. So MM usually go together. And the other two numbers, the M is the number of servers. Let me try writing that again. It's correcting me a little bit and not doing a good job. And that last number, N, is the maximum number that can be in the system or store. If that number is left off, then it's assumed to be infinite. So in general, we're mostly going to do with MM. Another example would be if you had, for example, an assembly line, then just something is finished every 30 seconds, and that would be a different type of distribution. It'll actually be slightly harder because I think I said at the beginning that if something is exponential and if something's Poisson, then it is what's called memoryless. So if it's exponential, if you waited in line for 2 minutes, the probability you finish up in the next minute is the same if you waited 15 minutes, and the probability you finish in the next minute. So we don't need to know how long people have been there to figure out what the expected time we're going to have to wait in line. So Poisson exponential makes that calculation part simple, whereas other types we'll have to figure out how long the person has already been there on average. So it's a bit extra calculation. So since we're not only doing it as an example, we're not going to go too far, so we'll mostly stay with MM. Any other questions? As I said, hopefully you can hear this. We are basically done, so that you're just staying around if you still have further questions. And as I said, I'll stay for a little while if there are further questions, but otherwise you're going to go away and I'll see you back Monday. So as I said, I'll wait for a few minutes. Let me know if you have questions. As I said, if you're still here, people are starting to leave. I will also upload the written out notes.